In this video, we'll talk about the normal equation, which for some linear regression problems will give us a much better way to solve for the optimal value of the parameters theta. Concretely, so far, the algorithm that we've been using for linear regression is gradient descent, where in order to minimize the cost function j of theta, we would take this iterative algorithm that takes many steps, so multiple iterations of gradient descent to converge to the global minimum. In contrast, the normal equation will give us a method to solve for theta analytically, so that rather than needing to run this iterative algorithm, we can instead just solve for the optimal value for theta all in one go, so that in basically one step, you get to the optimal value right there. It turns out the normal equation method has some advantages and some disadvantages, but before we get to that and talk about when you should use it, let's get some intuition about what this method does. For this explanatory example, let's take a very simplified cost function j of theta that's just a function of a row number theta. So for now, imagine that theta is just a scalar value, or that theta is just a row value. It's just a number rather than a vector. Imagine that we have a cost function j that's a quadratic function of this row-valued parameter theta. So j of theta looks like that. Well, how do you minimize a quadratic function? For those of you that know a little bit of calculus, you may know that the way to minimize a function is to take derivatives and to set derivatives equal to 0. So if you take the derivative of j with respect to the parameter theta, you get some formula, which I'm not going to derive, and then you set that derivative equal to 0, and this allows you to solve for the value of theta that minimizes j of theta. That was the simpler case of when theta is just a row number. In the problem that we're interested in, theta is no longer just a row number, but instead is this n+1 dimensional parameter vector. And our cost function j is a function of this vector value of theta 0 through theta m, and the cost function looks like this sum squared cost function on the right. How do we minimize this cost function j? Calculus actually tells us that one way to do so is to take the partial derivative of j with respect to every parameter theta j in turn, and then to set all of these to 0. If you do that and you solve for the values of theta 0, theta 1 up to theta n, then this will give you the values of theta that minimize the cost function j. Well, if you actually work through the calculus and work through the solution to the parameters theta 0 through theta n, the derivation ends up being somewhat involved. And what I'm going to do in this video is actually to not go through the derivation, which is kind of long and kind of involved. But what I want to do is just tell you what you need to know in order to implement this process so that you can solve for the values of the thetas that corresponds to where the partial derivative is equal to 0. Or alternatively, or equivalently, the values of thetas that minimize the cost function j of theta. And I realize some of the comments I may have made more sense only to those of you that are a little more familiar with calculus. So, but if you don't know, if you're less familiar with calculus, don't worry about it. I'm just going to tell you what you need to know in order to implement this algorithm and get it to work. For the example that I want to use as a running example, let's say that I have m equals 4 training examples. In order to implement this normal equation method, what I'm going to do is the following. I'm going to take my data set. So here are my 4 training examples. In this case, let's assume that these 4 examples is all the data I have. Okay. What I'm going to do is take my data set and add an extra column that corresponds to my extra feature x0 that's always takes on this value of 1. What I'm going to do is I'm then going to construct a matrix called capital X. That's a matrix that basically contains all of the features for my training data. So concretely, here are all my features. I'm going to take all those numbers and put them into this matrix X. Okay, so just copy the data over one column at a time. And then I'm going to do something similar for y. So I'm going to take the values I'm trying to predict and construct now a vector, like so, and call that a vector y. So x is going to be a m by n plus 1 dimensional matrix, and y is going to be a m dimensional vector, where m is the number of training examples and n is the number of features. And I have n plus 1 because of this extra feature x0 that I added. Finally, if you take your matrix X and you take your vector Y, and if you just compute this and set theta to be equal to X transpose X inverse times X transpose Y, this will give you the value of theta that minimizes your cost function. There was a lot that happened on this slide, and I worked through it using one specific example of one data set. Let me just write this out in a slightly more general form, and then later on in this video, let me explain this equation a little bit more in case it's not yet entirely clear how to do this. In the general case, let's say we have m training examples, so x1, y1 up to xm, ym, and n features. So each of our training examples xi may look like a vector like this. There's an n plus 1 dimensional feature vector. The way I'm going to construct the matrix X, this is also called the design matrix, is as follows. Each training example gives me a feature vector like this. That's this sort of n plus 1 dimensional vector. The way I'm going to construct my design matrix X is I'm going to construct a matrix like this. And what I'm going to do is take the first training example, so that's a vector, take its transpose, so it ends up being this long flat thing, and make x1 transpose the first row of my design matrix X. Then I'm going to take my second training example, x2, take the transpose of that, and put that as the second row of X, and so on, down until my last training example, take the transpose of that, and that's my last row of my matrix X. And so this makes my matrix X an m by n plus 1 dimensional matrix. As a concrete example, let's say I have only one feature, only one feature other than x0, which is always equal to 1. So if my feature vectors xi are equal to this 1, which is x0, and then some row feature like maybe the size of the house, then my design matrix X would be equal to this. For the first row, I'm going to basically take this and take its transpose. So I'm going to end up with 1, and then x1, 1. For the second row, I'm going to end up with 1, and then x1, 2, and so on down to 1, and then x1, m. And thus, this will be a m by 2-dimensional matrix. So that's how I construct the matrix X. And the vector Y, sometimes I might write an arrow on top to denote that it's a vector, but very often I'll just write this as Y either way. The vector Y is obtained by taking all the labels, all the correct prices of houses in my training set, and just stacking them up into an m-dimensional vector, and that's Y. Finally, having constructed the matrix X and the vector Y, we then just compute theta as X transpose X inverse times X transpose Y. I just want to make sure that this equation makes sense to you and that you know how to implement it. So, concretely, what is this X transpose X inverse? Well, X transpose X inverse is the inverse of the matrix X transpose X. Concretely, if you were to say set A to be equal to X transpose times X, so X transpose is a matrix, X transpose times X gives you another matrix, and we'll call that matrix A, then, X transpose X inverse is just, you take this matrix A and you invert it, right? It's equal to, let's say, A inverse, and so that's how you compute this thing. You compute X transpose X, and then you compute its inverse. We haven't yet talked about Octave. We'll do so in a later set of videos, but in the Octave programming language, or similarly in also the MATLAB programming language, is very similar. The command to compute this quantity, I guess really this quantity, X transpose X inverse times X transpose Y, is as follows. In Octave, X prime is the notation that you use to denote X transpose, and so this expression that's boxing in red, that's computing x transpose times x. P_inv is a function for computing the inverse of a matrix, so this computes x transpose x inverse, and then you multiply that by x transpose and you multiply that by y, so you end up computing that formula, which I didn't prove, but it is possible to show mathematically, even though I'm not going to do so here, that this formula gives you the optimal value of theta, in the sense that this, if you set theta equal to this, that's the value of theta that minimizes the cost function j of theta for linear regression. One last detail. In an earlier video, I talked about feature scaling and the idea of getting features to be on similar ranges of scales or similar ranges of values of each other. If you're using this normal equation method, then feature scaling isn't actually necessary and is actually okay if, say, some feature x1 is between 0 and 1, and some feature x2 is between, ranges from 0 to 1000, and some feature x3 ranges from 0 to 10 to the minus 5. And if you're using the normal equation method, this is okay, and there's no need to do feature scaling. Although, of course, if you were using gradient descent, then feature scaling is still important. Finally, when should you use gradient descent and when should you use the normal equation method? Here are some of their advantages and disadvantages. Let's say you have m training examples and n features. One disadvantage of gradient descent is that you need to choose the learning rate alpha, and often this means running it a few times with different learning rate alphas and then seeing what works best. And so that's sort of extra work and extra hassle. Another disadvantage of gradient descent is that it needs many iterations, and so depending on the details, that could make it slower, although there's more to the story, as we'll see in a second. As for the normal equation, you don't need to choose any learning rate alpha, so that makes it really convenient, makes it simpler to implement, and you just run it, and it usually just works. And you don't need to iterate, so you don't need to plot j of theta, check for convergence, and take all those extra steps. So far, the balance seems to favor the normal equation. Here are some disadvantages of the normal equation and some advantages of gradient descent. Gradient descent works pretty well even when you have a very large number of features. So even if you have millions of features, you can run gradient descent and it'll be reasonably efficient and it'll do something reasonable. In contrast, the normal equation, in order to solve for the parameters theta, we need to solve for this term. We need to compute this term x transpose x inverse. This matrix x transpose x, that's an n by n matrix if you have n features, because if you look at the dimensions of x transpose dimensions of x, you figure out what the dimension of the product is. The matrix x transpose x is an n by n matrix, where n is the number of features, and on most computer implementations, the cost of inverting a matrix grows roughly as the cube of the dimension of the matrix. So computing this inverse costs roughly order n cube time. Sometimes it's slightly faster than n cube, but it's close enough for our purposes. So if n is the number of features is very large, then computing this quantity can be slow, and the normal equation method can actually be much slower. So if n is large, then I might usually use gradient descent because we don't want to pay this order n cube time. But as n is relatively small, then the normal equation might give you a better way to solve the parameters. What does small and large mean? Well, if n is on the order of 100, then inverting a 100 by 100 matrix is no problem by modern computing standards. If n is 1000, I would still use the normal equation method. Inverting a 1000 by 1000 matrix is actually really fast in a modern computer. If n is 10,000, then I might start to wonder. Inverting a 10,000 by 10,000 matrix starts to get kind of slow, and I might then start to maybe lean in the direction of gradient descent, but maybe not quite. N equals 10,000, you can sort of invert a 10,000 by 10,000 matrix. But if it gets much bigger than that, then I would probably use gradient descent. So if n equals 10 to the 6, if you have a million features, then inverting a million by million matrix, it's going to be very expensive, and I would definitely favor gradient descent if you have that many features. So exactly how large your set of features has to be before you convert to gradient descent, I don't know, it's hard to give a strict number, but for me, it's usually around 10,000, but I might start to consider switching over to gradient descent, or maybe to some other algorithms that we'll talk about later in this class. To summarize, so long as the number of features is not too large, the normal equation gives us a great alternative method to solve for the parameters data. Concretely, so long as the number of features is less than 1,000, I would usually just use the normal equation method rather than gradient descent. To preview some ideas that we'll talk about later in this course, as we get to the more complex learning algorithm, for example, when we talk about classification algorithms like a logistic regression algorithm, we'll see that those algorithms actually, the normal equation method actually do not work for those more sophisticated learning algorithms, and we will have to resort to gradient descent for those algorithms. So gradient descent is a very useful algorithm to know, both for linear regression when we have a large number of features, and for some of the other algorithms that we'll see in this course, because for them the normal equation method just doesn't apply, it doesn't work. But for the specific model of linear regression, the normal equation can give you a alternative that can be much faster than gradient descent. And so depending on the details of your algorithm, depending on the details of your problem and how many features you have, both of these algorithms are well worth knowing about.